Hey guys, are you ready to deep dive into dynamic NodeGraph implementation in C++ and Rust? In this episode, we will look into an implementation of the dynamic NodeGraph which will be complete, which will be safe, will guarantee the safety of pin connections. So in case a node has disappeared, the pin connection to that node will not cause any crash. There won't be any dangling references, and we will get Rust to compile our code and run it. Let's start with a recap of what NodeGraph is and how it works. This is our NodeGraph, a simple one. In this NodeGraph we only have 3 nodes. We have a source node, destination node, and transformation node. Each of the nodes has pins. Source node has this output pin, destination node has this input pin, and the transform node has the input pin and the output pin. Additionally, transformation node inside has some function that will process data that comes from input pin, and the result will go into the output pin. The execution of the node graphs can go 2 directions. It can go forwards or it can go backwards. When execution goes forward, then source puts a new value on the output pin and then sends this value to the input pin of the connected node. This value is then received by this transform node. A function is applied, and the result of this function is sent to the output pin of this transform node. And then the output pin of the transform node sends this value into the input pin of the destination node, which will then ingest this value. Graph can also be executed backwards. And here is how it goes. Source node puts the value on the output pin. Now, the destination node requests from the input pin to receive data from the connected pin. That pin is an output pin of the transform node. Then transform node will ask its input pin to receive the data. And then the input pin will ask connected pin for the data. It will receive this data. Then this data gets to transform node. A function in transform node is applied over this data, and the result is sent to the output pin of the transform node. Then the input pin of the destination node will receive this data, and the destination node can ingest this data. Alright, so what are the difficulties with NodeGraph? So the main difficulty with the NodeGraph in C++ and Rust is potentially dangling references. So if I were to remove this node from the graph, I still have these connections. I would still have connection from this pin to this pin, and I would still have a connection from this pin to this pin. So these 2 connections are essentially pointers to an object that stopped existing, because this whole object of the transform node now is gone. We just deleted it from the graph. And we have very unsafe situation when this happens. So what do we do to prevent this problem? In C++ we have shared pointers, and we'll discuss advanced features of shared pointers. An advanced feature because the pin is a member of a node. It's a member variable, it's part of its memory layout. So if there is a node in memory, then somewhere inside this node structure there is data that's pin structure. It's in the same memory, it's not a different memory. So the whole thing is allocated as one allocation. Now, if you want to have a pointer to this node, and if you want to have a pointer to the pin, we can see that this pointer to the pin is pointing to the internal part of this node. But we said we want to keep nodes in shared pointers. If this is a shared pointer, and it points to this beginning of this node, how can we make a shared pointer to a pin? As it turns out, C++ gives us a tool to do that. We can convert one shared pointer into another. There is a constructor to do that, and we will learn about this constructor today. Additionally, there is another issue. Let's take this transform node, for example, now. And there is this pin here, okay? And of course this other pin as well. So this is one fragment of memory together with those two pins, okay? And this is another fragment of memory. So these are two fragments of memory, blue and red, but they are continuous, right? So there's a continuous red fragment of memory and there is continuous blue fragment of memory. There are two different continuous fragments of memory. Now we have a pointer to this node transform node, and we have a pointer to this destination node. These are shared pointers, okay? Now, if we establish a shared pointer from this pin to this pin, and then from this pin to this pin, we are creating a cycle. And we know that shared pointers don't like cycles. So to avoid the problem of cycles, we will be using weak pointers. The pins will still use references to its parent nodes, because parent node will not vanish, leaving the pin with dangling pointer, because this is one piece of memory. So using a reference here is okay. It is safe to do so in C++. We will use weak pointer here and here to avoid cycles. And we will use shared pointer here to keep the ownership of the nodes. Alright, let's see how this works. So when we remove one of the nodes from the graph, then this shared pointer no longer points to that node, and then this pointer here would be a dangling pointer. But because it's a weak reference, it will automatically know that node is gone, and it will know that this connection is now disconnected. Let's look into the code to see how this works. So this is the version of our dynamic node graph from our previous episode. Our node graph was storing nodes via unique pointers, but we know that unique pointers weren't good. They weren't good because if I store nodes by unique pointers, then if I remove the node from the graph, then I have no way of pointing into that node in a way that is safe. I have to use row pointers. And if you look at how pins are implemented in this version, it is a row pointer to a pin. Alright, so let's see how a new version looks like. So this is our new version. I won't be typing this time, I will just scroll to the code. Alright, so what we have here. We have now shared pointer. Okay, so node will list as pins as shared pointers, as set of shared pointers. And pin will have getConnectedPin method returning a shared pointer. And you can see it does connection lock. And connection is a weak pointer. So why like this? So whenever we want to access the content pointed by weak pointer, we have to lock it. And as a result, we're getting a shared pointer, as we can see here. And this is because when we ask if the weak pointer is pointing to some valid memory, it has to be in transaction with what we're going to do with that memory. We cannot ask if weak pointer is valid and then just use the pointer, because in the meantime, the memory might become invalid. So to prevent this from happening, we need to lock it. This lock is simply getting from the weak pointer a shared pointer, meaning that we will increase references and the pin stays alive, and as we will learn, also the node will stay alive. Because this pin, as we can see, cannot stay alive if this reference to a node becomes invalid. Right? So somehow this shared pointer to a pin will also keep the node alive. How does it work? So you can see I have implemented shared from this for the pin, and I have enabled shared from this for a node. Okay? So if you use std enable shared from this, then inode gets two methods, shared from this and weak from this. For the pin class, I have implemented shared from this by hand, because what I want from pin class is to use its node shared pointer. So when we ask for a shared pointer to a pin, we are not getting a shared pointer of a pin, but we're getting a shared pointer of a node memory, which includes the pin. But then here we pass this. This is a specific constructor of shared pointer, when you can say I have a piece of memory pointed by this shared pointer that is managed, Okay. So for this piece of memory, there's some ref count, but then inside of this piece of memory, I have some field, and I want to point to this. Okay. There is also an option to point to something completely else here. Okay. And somehow maybe these things are connected to each other. The idea is that this resource, this here, that I'm passing to shared pointer constructor, is somehow related to this shared pointer, the original shared pointer, right? So the original shared pointer controls the control block. And in this control block, it has information where is the beginning of the memory slice that is to be managed. And then the other pointers that we provide here, in this new shared pointer, the new shared pointer will assume that this other pointer lives as long as the slice of memory pointed by this shared pointer here. In our case, this is a very trivial case because we have a node with this pin, okay? And this pin is part of a node. So if this is the beginning of our memory that is managed by shared pointer, then this pin is just part of this memory. So what happens when all the shared pointers pointing to this beginning of this memory die, and we still have a shared pointer to this pin? What happens is that this pointer has a control block that is pointing here, and the pointer that is pointing here. So it knows the reference count of the whole node, okay? But when you ask it to give you a pointer, it gives you a pointer to this pin and not the node. This is a very clever solution and very useful. Unfortunately, I couldn't find an equivalent in Rust, and I had to resort to a different solution in Rust. Alright, so this is the implementation in C++. As a result of this implementation, there are some consequences. So we obviously use now shared pointers, and we store weak pointer. The node graph is now storing nodes as shared pointers, and that's basically it. Okay, so that's the change. Now let's look at another change, because in this example here, we're still connecting nodes in a static way. You see the add example nodes to graph is still making these connections here. What if I would like to be able to make those connections dynamically? Ultimately, NodeGraph is a tool for user interface. A user would create a node with some pins, and after that, user would connect the pins. How can we do that? So let's look at this next implementation and the changes we've done here. What was added here is a try-connect method into IPin. So now we have a function that allows us to try connect one IPin with another IPin. Note that this IPin, this interface, doesn't have any type of a pin actually. So we're connecting two abstract pins. And we know that this is not always possible. We have to connect input pin to the output pin, and the types they carry have to be the same. Let's look at the picture. The type of data here has to match the type of data here, right? So the output pin and the input pin, they have to be connected in a way that this data can be copied over to this place here, right? So try connect function will try to see if pins are matching, and if they're matching, then they will connect them. So you can see that try connect is implemented for input pin, and it's also implemented for output pin. What try connect does, the implementation for the input pin is below. It's here. So try connect for the output pin, for example, has to check if the pin is an input pin for T. Okay, so output pin for T accepts only input pin for T, whereas the input pin for T accepts output pin for T. So this is the way these connections are established here. All right, let's see how the example looks like now. So we can see that now we're building the graph without connecting pins. So we just add nodes. And now we have a little bit more involved example, which has to dig the pins out and, do the connections. So we can see here, we got the target nodes. Then For the target node, we get the input pins. We also get transform nodes. There's only one. We assert that there's only one because this example, kind of like a test, kind of like an example. This is just for presentation purposes, right? So we have a transform node, and for transform node, we're gonna get pins for input and output, and then we're gonna connect them here by doing try connect. So when I'm doing transfer input pin try connect to source pin, the connection goes in this direction, okay, backwards. So we're connecting the input pin to the output pin. And when I'm doing try connect target pin, I'm going the other way. I'm connecting output pin with the input pin. Okay, so this way I kind of present two different directions in which pins can be connected. Of course, I can connect the input pin of the destination node to the output pin of the transfer node as well. This is just for demonstration. All right, so we have this code, and after these connections, we can proceed as usual, load the value, process forwards, load the value, process backwards, and see what will happen. So in this example, we use example data sample and example data result. We change the type of data in this example from simple floats into data structures to demonstrate that bigger data structures can be handled also efficiently. So what we did here, when we created nodes, we created them for shared pointer of example data sample and shared pointer of example data result. Why do we need shared pointer? So as we remember from previous episodes, when we receive or send data between the pins, we copy the data in this implementation. So when we set data here on the output node of the source node, and then we send it to the input node of the transfer node, we literally copy the value, okay? So that would be inefficient if it was a big texture, for example. But we can make it a shared pointer, and then texture lives here separately in some memory on the heap. And then shared pointer here is pointing to it, and when we copy shared pointer, we just increment references, right? If the new value is put on the source node, then it is shared pointer to some other texture, and this one is gone, right? So we have one reference here and one here. In this example, I'm demonstrating that holding on to a pin of a node that was removed from the graph will not cause any dangling pointers. This is my shared pointer to a source output pin. I assign it somewhere here, and then this is the scope within which the NodeGraph exists. You can see the NodeGraph is living here, the nodes are created here, and this is how long the NodeGraph would live. But then here we are accessing source output pin. Okay, let's see if that will crash. Alright, so this is the output of this example. So we can see that after destroying NodeGraph, the source node destructor is called. Okay, so this is the previous example where we didn't hold on to any pin, and you can see the order of destruction is NodeGraph, target node, source node, transfer node. And this is our new example where we hold on to one of the pins and we keep the reference to that pin after destruction of the graph. And we can see that after destroying NodeGraph, we still have the pin, okay? It says it's not connected, it knows that it's not connected, the graph is gone, the pin is not connected, and the owning node still exists, right? So this is the most important because the pin is part of a node, and pin has a reference to a node. When I say owning node, you know, I'm accessing the reference to the node. So if this didn't work correctly, then this owning node would cause a crash. And we can see that at the end of a scope, we have a destructor of source node called. Alright, so this is our dynamic node graph, which will work perfectly for single-threaded applications. In the next episode, we will look into forking. Our current node graph version is very simple, it's just sequential. But what if we have another node here and we want to connect it like this? We need to make sure that this input here gets copied over here and here as well. And this needs to work in back propagation and forward propagation. Alright, but this is material for the next episode, and now let's focus on Rust. Right? Okay, let's see what we can do in Rust. Alright, so this is dynamic NodeGraph implementation in Rust, which compiles and works, as we can see on the picture. Okay, so how does it actually work? In this implementation, I have defined new GraphNode pin-based trait with Downcast capability, and I added Downcast capability to the GraphNode, okay, so that we can downcast the GraphNode into specific node, and we can downcast pin to specific pin, okay. The GraphNode pin base has try-connect method, isConnect and disconnect. Same methods as we've seen for IPin interface in C++. The GraphNode has now new methods, get inputs and get outputs. And these methods return option vec rc din GraphNode base. What does it mean? Well, they return option so that we can say there is something or there is nothing. They return vec so that there is more than one. Okay? And they return rc din GraphNode pin base, which allows us to return abstract pins, which then, if we need it, we can downcast a specific type of a pin. You can see that there is impl downcast here to implement downcast for this traits. Okay, we have changes to GraphNode pin implementation, so you can see that node is no longer a reference with lifetime. Now it is a weak box din GraphNode. So in this Rust implementation, this is weak and this is weak. It's not a reference. Then we have connection, which is refcell option weak GraphNode pin of t. So it has to be refcell because we want to dynamically change it. It has to be option because connection can be either there or not. And it has to be weak because, as we have seen from C++ code, we don't want to have cycles here. So we implemented those connections between pins in the same way as we did in C++. So we use weak references to prevent cycles here. So we can see that the GraphNode pin now has a constructor which takes weak box din GraphNode. Okay, so din GraphNode needs to be in a box in order to be weak. We could complain that type is not sized, so that's why it is in a box. We create the node with no connection and default data. We can see the equivalent from C++ here for the get connection. We remember in C++ we used lock on the weak pointer. Here it is a little bit more involved, so we need to borrow this connection because connection is in ref cell. Then we have to treat it either as ref or clone. So this option here with this weak, we need to either clone this option or just get a reference to the weak inside. Then we have to unwrap it so that we just get the weak reference. And then we tell it to upgrade itself to the RC. And this is how we get, RC. Okay? And funny enough, we don't have to wrap it into option because upgrade itself, as we can see, returns an option, which is pretty cool. Because for the node we also use weak, as we see here, we also have to upgrade when we call getNode. And we get option RC box then GraphNode. We have some implementation for isConnected and disconnect. There is some match here whether connection will match some. So upgrade gives us an option with RC and GraphNode pin inside it, right? So you can see. Alright, so let's see what else we have here. There's some little changes to just make it compile, and then we have a try connect. So try connect is implemented in more or less the same fashion as it is implemented in C++. In C++ we used dynamic cast, and here we call it downcast ref. Okay. We have parameter other, which is rc din GraphNode pin base, and we need to make sure that if it is if we are the input pin, then the other has to be the output pin. So this is what we do in this downcast here. And if we are successful, then we call connect. We have a concrete type in this case. Otherwise, we just error with some text telling us the name of a type. So we use std_any type name for t to get the name of a type here. The difference between C++ code and this Rust code is that we cannot have an RC to some offset address in the memory that's pointed by another RC. So because of that, I have to have pin in the RC here. So we have node input pin having an RC with graph node pin. Okay, this is a little bit tricky here. But then to avoid creating too many RCs, the output pin in the source graph node is kept by value as is. And then we have to implement this get inputs and get outputs, and inputs, there is no inputs for the source node, but there's outputs for the source node. So you can see what we're doing here. I'm putting this output pin into a brand new RC. So what I'm doing is, when you ask me to give you the outputs, then I'm cloning those output pins into a new RC. So this way I'm having an RC. As a result, I'm having an RC of graph output pin, which contains RC of graph node pin. So this is kind of convoluted, but yeah, so at least I don't have to store RC in here, And we can do that because this is one and only reference to this clone, right? We know that the output pin doesn't have any members of our interest. Our output pin is clonable because the only member is the RC to the graph node pin. I did the same for the target node. So you can see we have the graph node input pin as by value, and the get inputs now is returning RC made out of the clone of that. And then for transfer node, of course, I did the same thing for inputs and output. Now, the interesting part about all those nodes is that you will see this RC new cyclic, and that's the new one. So let me just, this one is complicated. Well, it's just because there's two pins. So let's look at the source node. So in order to construct graph node output pin, now we have to construct graph node output pin from, RC new graph node pin me. Okay, so what that means is I'm doing new, and I need to pass some sort of reference into this pin that I'm creating to myself. But there is a function in RC which is new cyclic, which takes this constructor function that takes the me argument, which is a weak reference to me, and then I can use that me and clone it. Okay, I can clone this weak reference, so that will just increment the number of references to me, and put that me inside this newly constructed graph node pin. Okay, and that will be the back reference to the node. So this is how we construct this back reference here. This new cyclic with this piece of code here will do exactly that. Okay, so what this new cyclic does is whatever type you have here, okay, it will return. So you can see that we're returning RC boxed in NodeGraph, so that's our return type. And this is what we are constructing inside of this function that we pass to new cyclic. So this is exactly the same thing. So you have box new, okay, so that's our box. And then we have this graph node. So this self is a, source graph node is a graph node. Source graph node is implementing the graph node trait, so we can put it as din graph node. So that's our self, and then the the self stuff. And we get the me from new cyclic, right? We get the me. So that's how we solve this cyclic reference, and everything works now, and no problems with lifetimes anymore. Right. So what else I did? I created this test functions. Okay, so this is my my test. We can run it. You can see 100, 400. The input was 10 and 20. The function we used was square, as we can see. So this is correct. So the node graph was correctly, surprise. Build node graph simply creates the nodes, put them into node graph, okay? So yeah, so I don't want this, I want just this. Okay, so we're creating a node graph. You can check that this is valid still. Yeah, it's all good. Did I ask Clippy to check? Clippy doesn't like us. Why? Oh, he doesn't like that I call the method new and it doesn't return the self. Okay, we can change this. How do we call it? New RC? Let it be new RC. What Clippy is complaining is that if I put clone after iter before filter, I'm cloning all the nodes and not only the ones that I have filtered, you know? And if I do it after filter, then I'm cloning the nodes that are only the results of my filter, which is good. All right, perfect. Okay, and this cloning is just an increment of reference, but because these are RCs, but even that takes a hit on performance. So, you know, doing less is better. Okay, of course, this is new RC now. All right, perfect. Look at that. We made Clippy happy. Can you imagine? How can you not love Rust? It has Clippy. I mean, everything is so nicely integrated, and I like the fact that it's complaining so much because, yeah, I like when it compiles, it works. Except that it actually didn't. My previous version, and it was compiling and it didn't work because, well, there is dynamic aspect to it, right? So this downcast and so on, that was all okay, but I didn't implement correctly try connect, right? Because I need to connect both directions, the pins, you know? So this way, when try connect is implemented for input pin and for the output pin, then this connect here, you see it connects both directions, bidirectional. But the connect inside of a graph node pin, this connect here, it makes only one direction connection. And the problem with this is if I was implementing that trait for graph node pin and not graph node input pin, then try connect implemented for this would just connect in one direction, right? And calling try connect for the other pin would be inefficient. So like if I were to call, you know, try connect on the other pin, that's something I didn't want to do. So I just implemented try connect for input pin and output pin separately. So also I needed try connect to check if I am the input pin, then it has to be output pin, and if I am the output pin, then I want it to be input pin. So this is more like semantics, because this input pin and output pin is just an RC to the node pin, you know. So it's just a kind of wrapper. All right, so what else we're doing here? We have this node graph here, and then we have this build some graph. And build some graph, you see source graph node, new RC, new RC, new RC. Okay, we create nodes and put them into node graph. And then I also have connect some nodes, and that just makes some assumption about the graph, because it's our example. You see, it is just test. So the assumption is that the graph looks like this, so there is just 3 nodes connected like this. So I get the first node, it gives me the option, and then I will turn the option into result using OKR, and that helps me use this question mark here, which will exit this whole function because it returns result. So this question mark will take this error result and exit immediately, and if it's success, it will clone the value. So that's what it does. Okay. So this is our example. So in the example we say, let's build a node graph. So this is this create the nodes thing. Then let's connect some nodes. Okay, so this is this guy here. So we connect the nodes. We have the connect result. We assert is okay. And then we get the source node and target node from the connect result. We return them here in this connect some nodes. And we downcast into concrete types. And this is our final test. So we load value into source node source, I call it. I didn't have a better name for it. So that would be our value loader for the source node. Then the other case would be target node, target get value. So load value into the source, process forwards, and get the value. Or load value into the source, process backwards, and get the value. So we have both dynamic node graphs now in C++ and Rust, single-threaded. And we will have to look what happens with this node graph in multi-threaded scenario, right? So in multi-threaded scenario, we will have a situation where we are changing this value here. When we are changing this connection, and this is a weak pointer, so we have to have some sort of atomic way of doing it, because of course refcell isn't, thread safe. So, that will not work if we try to create example in Rust. If I try to create in Rust an example which tries to do changes to this connection on different threads, it will just say that it's not send, right? Refcell isn't send, I suppose, which is a very cool thing in Rust. I think the traits guarding whether type can be transmitted between threads, that's really cool that we have those traits, I invite you to the next episode, which probably will be about forking.